Okay, so for today's topic, we're going to go over force vectors. And we're going to start by going over a little review of the difference between scalars and vectors. So scalars, I'm going to kind of read from this a little bit and then explain what's going on. But basically, we can have a positive scalar or a negative scalar, but it's a quantity that only is associated with a magnitude. So it's just basically a number with its units, but there's no direction associated to this type of quantity, okay? Some examples of this are length, mass, or time. So when you think about length, how long something is, it doesn't matter which direction you're measuring it in, it's going to be the same length. Whereas a vector is something, excuse me, that we define by having a magnitude and a direction. So something, for example, position, the reason we need to know direction is because it starts from some reference point. A position has to do with your reference point, okay? And so this is why we need to know which direction that is associated with. Typically, in this class especially, actually, whenever I'm talking about a scalar, I'll just be writing the notation for it like this. And when I'm talking about and it can be any variable, it can be f, whatever the variable is, it'll just be a regular variable that looks like this. Whereas for a vector, I would be putting an arrow on top, okay? This is in contrast to anything typed where you would see a bold letter. I can't write a bold letter, so instead, when you're writing, you can just write a vector with a little arrow on top. Okay, and that's why I put represented by an arrow. The length of that arrow typically represents the magnitude, and then our angle with some axis represents our direction. Okay, we'll learn in a little bit how our direction can also be represented by using, this might be familiar from calculus, or I hope it is, but our I, j, and k vectors, which represent the x, y, and z axes of our 3D coordinate axis system. And, oh, I already wrote this for you guys here, yeah. We usually represent a vector by a letter with an arrow as such, or by a bold letter. Okay, so a resultant force is basically the difference between all of the forces acting on an object. And when I say difference, that could be addition or subtraction. So for example, if I were to have some object right here, let's just say this is some ball or something, whatever, and I would have a force tugging on this object in this direction that's equal to 10 pounds. Okay, and let's say I have a force tugging on the ball in this direction equal to 10 pounds. So you could think of the resultant force as our net force. And this is why force is a vector, and this is why vectors are so important. Because here, if I were only to consider magnitude, I could say, oh, well, there's 20 pounds of force acting on this ball. But that's not actually true, right? Because what's happening here is I have 10 pounds of force acting to the right with this arrow, and I have the equal force acting to the left. So what happens is the forces actually cancel out, and my resultant force is actually 0. It's not 20, right? Because force is a vector. Okay, force is a vector, so direction is important. So really, if I wanted to write this out, let me show you how I would write this out. These will get a little bit more complex than what I'm drawing now, so I'll show you here. Typically, this is a preview for later. Typically, I would have my x-axis and my y-axis, right? And what I can say is, well, this 10-pound force acts on the positive x. This negative 10-pound acts at the negative x. So what happens is I would have 10, it would be positive, so I'd have a positive 10. And this is resultant, right? This is the resultant force. And then here I'd have negative x, which means I need to subtract 10. And that's how I get that 0. That's how I would actually write that out. Okay? Oh, I guess I kind of already did this example. No, not really though. We'll do it again actually because it's a little bit different. So here, I want to know what is the resultant of the two 10-pound forces shown, Okay, and remember we have to include magnitude and direction here. So what we're gonna do, I already have the positive x and positive y set up for you here. So let's do this. I'm just gonna call this force resultant equals this first one here. It doesn't matter which one goes first. This first one here, it's going to be a positive 10 because it's being pushed in the right direction. So positive 10, and then I have another positive 10, positive 10. My answer is positive 20. Okay, now I'm going to say this a lot, but I'll give you a little preview of it here. So when I put the positive or negative, in reality, the world or forces don't really work with positive and negative. That is a convention for us to use that makes these problems convenient, right? The force doesn't really, I mean, there's a 20-pound force on this object. It doesn't care which direction it's coming from. It's feeling a 20-pound force. What the positive does and the negative does is it tells us which direction it's in. So this is for our record keeping and track. Okay, so what this means here is if I get a positive answer, which direction is my force, my resultant force acting in? I'm going to take away the positive and say 20 pounds to the right. And this is my final answer. Okay. Now, I don't think I have this here, but I'm going to ask you guys a question. So what if my forces were going in this direction? Okay. Ignore the red here. We'll say they're going in this direction. Right? Okay. I would have negative 10 minus 10 equals negative 20. My answer would be the resultant is equal to 20 to the left, 20 pounds to the left. Okay. And that's how I would write that. All right. We'll do one more example here. So if I have 10 pounds going up, another 10 pounds going up, now my final answer, so my resultant force would be positive 10, because it's y, plus 10, which would be positive 20. And now we can just visually see which direction am I going to put. My FR is equal to 20 pounds going up. So you see how this answer is different than the first one, right? Direction matters. Okay, so now my question is, what if I have a vector or two vectors that act in different directions? So what if I have a vector here in this direction and a vector that acts here in this direction or something like this? How do I find the resultant of two vectors that act in different directions? Because remember here, we're adding vectors that act in the same direction. So what happens when I have a system like this where I have to combine vectors that act in different directions? So I want you guys to take a minute, actually, you can pause this video and try to fill in numbers 1 through 5. What steps did you take? And the reason I'm asking you to do this is because you've already done this in physics and in calculus. So this needs to be a little bit of a refresher for you. We're not going to spend too much time on it. So I really want to get your memory working and make sure that you can come up with these. Okay? So hopefully you've paused and you've kind of filled these in. But the first thing that you should have here is you need to put each vector, right? Typically, you need to put these vectors into x and y components. This is one method, by the way. This isn't the only method. We'll go over a couple. But this is the one we'll probably be using more or most of the time in this class, and that you'll use a lot of the time in mechanics of materials and in structural analysis, okay? So put each vector into their respective x, and this is, again, this is for 2D systems. We'll talk about 3D later. X and y components. Okay. Now what we want to do is we want to add the x components together. And this would give us our forces in the x direction. And we can do the same thing with the y. So we'll add our y components. And this will give us our Fy. And our resultant, I'll call this Fr, is equal to the square root of fx squared plus fy squared. That's our magnitude. And our direction, theta, would be equal to inverse tan of whatever the component in the y direction is divided by whatever the component in the x direction is, and this is my direction. Okay, so very simple. And we're going to try this now with another problem. But first here, this is just a picture of what the resultant force looks like. So here, remember, this is super important. We have to be really good at our vector analysis and our trigonometry here. Okay, you don't need to remember all of trig, but you do need to remember a couple of key and important factors of trig. So I'm going to go over those pretty quickly here, just as a kind of refresher. If I'm given an angle theta, if I'm given an angle theta right here, what I want to remember is, if you guys, I don't know if you guys learned it this way, this is how I learned it, but if you remember SOHCAHTOA, right? So the O stands for opposite, H is for hypotenuse, A is for adjacent, okay? Opposite, if this is my triangle and this is theta, what would be opposite of theta? This is my O. What would be adjacent to theta, right? And then the hypotenuse of the triangle is here. Remember, that changes if my theta changes, right? That changes. So if my theta, this is a really messy drawing, I just want to show you guys. If my theta is here, it could be the same triangle, but now my hypotenuse stays the same, my adjacent is here, my opposite is here, okay? So it does not have to be that cosine goes with x and sine goes with y. You need to know which angle you're measuring it from, okay? And I'll show you this in a couple of examples, but for now, let me use the one we have here. So if I'm looking at this triangle here, okay, this one that I just outlined in red, and I have my theta right here, this is going to be my adjacent side, this is going to be my opposite side, and of course this will all be my hypotenuse. So fx corresponds to the adjacent side. So I'm going to come here, which is the first three-letter term that has an adjacent? It's going to be ca, which stands for cosine, right? The C stands for cosine. So this here is equal to, let me get a different color here, equal to F, which is the resultant, cosine theta. My Y is equal to F sine theta. Okay, if this was a little bit confusing, make sure you go back and review this part of trig, which helps you put your or any vector into components. Okay. Now this is another way of viewing this. So sometimes we'll get angles, sometimes we'll get lengths, sides. Okay, so we'll get like A, B, C, right? So again, we can do something similar. We see here that we have a length A, so our f of x here is just going to be equal to f times the one that corresponds to that same side, right? So we're doing the horizontal side, so A over C, whereas this is going to be equal to f times B over C. So we're able, oh, I already wrote those down here, yeah. So we're able to, oh, and yes, this is negative. We're able to put these into components and figure everything out this way. And so make sure, yeah, don't forget the negative sign like I did. The negative is important because remember, these are vectors and direction matters. Okay, so let's move on. Resultant force is continued here. Basically, what is the resultant in the x direction? Well, it's the sum of all of my forces in the x direction. Resultant in the y, sum of all my forces in the y, and this is basically what I've already written down for you in those 5 steps above. Okay, so we're going to go to an example here, and I'm going to show you how to solve this using the methodology that we just kind of talked about. So we have a screw here subjected to 2 forces, F1 and F2, and we want to know what the magnitude and direction of the resultant force is. So there are a couple of ways to solve this, and I'm going to go over a couple of different ways in the next couple of slides, but we're going to do this the component way that I just talked about. You can also do something called the parallelogram method or the triangle method, which we'll go over. And then once we kind of go over all the methods, you're free to use whichever ones you want to solve problems. Okay. So here, what I'm going to do, I'm going to come and take the F1 equals 100 Newton force and put it into components. So the first thing here, I'm going to start at the origin. I know that I have an F1, this will be cosine 15. I can put the 100 in too. I can either put F1 or 100, whichever one you guys like. Maybe let me put the 100 so we know. Okay. And if I have that component, I need to also put my component here, which would be 100 sine 15, because it's opposite. And I'm going to use a different color here. I'm going to use pink for the F2 vector. And I'm going to start at the same point. I'm just going to draw these a little smaller because I want to show you the differences here. So I have 150. Now, my angle is measured from the y-axis now. So that is no longer adjacent. This would be my adjacent, right? So now this has to be sine of 10. And this one here, I know these lengths aren't right, but I just want to make sure you can see both arrows. So 150 cosine 10. Okay. So guys, I cannot stress enough how important it is to understand this. Okay. I know this may seem basic for some of you. It may seem a little advanced for others of you. If this didn't make sense, please reach out to me. Okay. We'll go over some vector analysis, and you need to make sure that you can do this because a lot of the stuff you're going to learn in this class is really dependent on your next class, or your next classes are really dependent on them. Okay, so for example, when you move on to mechanics of materials and structures, this stuff needs to be done in a matter of like a snap of your finger. It needs to be super quick because you have to move on to the rest of the examples. So make sure you take the time to understand what's happening right now so that it doesn't compound later. Okay, I cannot tell you guys enough how many times I see students in other classes understanding the material but lacking the statics and they can't even move forward. Okay, so don't do that to yourself. These are simple examples. Just make sure you understand them before moving on, okay? So now what we're going to do is we're going to sum everything in the x and y direction. So let's start with x. What do I have in the x? I'm going to highlight it in yellow. I have this and this. So I would need to take the 100, it's positive 100 cosine 15 and positive 150 sine 10. They're both in the positive x direction. And I just have to add those up to get the resultant. Newtons. We'll do the same thing in the y. Both positive. And also in newtons. And then my resultant, I have to call these FR, is just going to be the 122.6 squared plus 173.6 squared. And I end up getting my resultant force is 212.6 newtons. Okay, now let's do the angle theta. And this is measured from the positive x-axis. So my resultant force is, this was 15. Let's say here, this is some theta. It is 54.76 degrees and has a magnitude of 212.6 newtons. That's my resultant force right there. I think I drew that a little bit too much to the bottom there, but that's okay. Okay, so let's move on now to vector operations. So this is also kind of a review of what we can do with vectors, Okay, so that was one method that we can use. We can put everything to the x and y components, and that's the method that we're actually going to be using a lot in other applications of engineering and a lot in this class. But there are two other methods that you need to be familiar with, at least for these beginning topics, because they will help us solve different kinds of problems, okay? So the first operation is vector addition. And we're going to go over the parallelogram law of addition. Okay, so let's say I have two vectors. I have a vector here. I'm going to call this vector A for simplicity. And then I have a vector here, vector B. And basically what I know is I know that I want to add A plus B to get some resultant. Okay, and how do I do that? How do I get the resultant of A and B? By adding. So what I do is I'm going to take both vectors and have their tails begin from the same point. So I'm going to draw A right here. I'm going to draw B connected right here. Okay. Now what I'm going to do, I'm going to draw a line parallel to B that touches the tip of A. Okay. And I'm going to draw a line parallel to A that touches the tip of B. Just like that. So I know that my lines are not 100% parallel, but they're supposed to be. So this line here should be parallel to this line. This line should be parallel to this line. And if you guys can see now, this guy here, this quadrilateral, forms a parallelogram, which by definition is that each opposing side is parallel. Okay? So now what we can do here is we start from the tip again and we draw a line diagonal to the intersection, and this here is my resultant. And that's it. It's really that simple. Okay, so we can use the parallelogram law of addition to add vectors. You'll get the same answer that you did by adding them in the xy components, but sometimes it's much easier to use the parallelogram law than it is to put everything into components, and sometimes we have to use this rule. Sometimes it's just too difficult to solve the other way, so we will be using this sometimes. And the other rule that we can use, rule 2 I'll call it, is the triangle rule of addition. It's very similar, but as you can tell, or as you can predict, it's going to be using a triangle. Triangle law of addition. Okay, so I'm going to start out with the same vector system, A and B. And what I'm trying to do is figure out how to get R. So now what I'm going to do, instead of drawing them like this with the parallelograms where they start at the same initial point, the tails start at the same point, what I want to do now is I want vector B to be added to A in something we call a head to tail manner. So just for reference here, if this is a vector, this is my tail, and this is my head, right? So what I want to do is I want to connect the head of A to the tail of B. So let me start by drawing A. Okay, so this is the head of A, right? So I want to connect the head of A, this is the head of A, to the tail of B. So I'm going to put a tail here, and I'm going to draw B. You guys see how I just kind of like took B, same direction, and put it right there? And now this here is my resultant. okay? And my resultant R is equal to A plus B. And then of course we have the cumulative property of addition, so it doesn't matter if you were to do this, the head of B connected to the tail of A, you'll get the same thing if you were to do it the other way as well. So it doesn't matter which vector you choose as A and B, as long as you're connecting the head and the tail of one to the other, then you're fine. Okay, so we can use both of these rules to help us solve for problems. Now we're going to move on from vector addition, okay, to vector addition of forces. So let's now extend this discussion to adding forces through vector addition. Okay, so again, what we want to do here, we have number 1, which would be finding resultant forces. We have 2 things that we can do here. We want to find resultant forces. But a second thing that we want to do in this category is we want to find components of a force. I'm going to be able to do both of these things. They kind of go hand in hand though, right? Okay, so if I want to find resultant forces, I'm going to highlight both of these. If I want to find resultant forces, let's say again I have some force F1, some force F2, right? I can do the same thing here. I can use the parallelogram law. So I'm going to draw a line parallel to F1 from F2, line parallel as good as I can. And I'm going to say that this guy here is my resultant force, FR, right? And my FR is equal to F1 plus F2. Okay, and I can do the same thing. I can extend this, right? This is the same as the vector addition. It's just with forces now. So I can do the same thing because forces are vectors. The head of one to the tail of the other. And I end up getting the resultant like this, right? And then what I can do here is a lot of times I need to apply the law of sines or the law of cosines to solve, because you see this triangle is not a right triangle most of the time. Or I should say it's not even often a right triangle, so not always a right triangle. So I can't just use sine and cosine. So what do I do when it's not a right triangle? I use the law of sines or the law of cosines. To solve for FR. Okay. And then to find components of a force, all I have to do, so sometimes we can resolve a force into 2 components. So we want to resolve one force into 2 components. Now we've already done this in a previous example using the x and y, but the idea here is what if we want to use any different axes? So what if I have a force and I actually want to resolve this force into this axis and a perpendicular axis, right? Or along this axis here, right? So I can choose some u and v axes. I can do this on any axes, and I'll show you what I mean by this. And to do so, I would use, again, the parallelogram and triangle laws to do this. Okay, so I'm actually going to show you this example here, resolving a force into components along 2 different axes using the parallelogram law and the triangle law in this example here. Okay, so right here we have a 600-pound force. And what we want to do is we want to resolve this into components in the given directions here. So we have a u direction and we have a v direction. The u direction acts along, I'll draw this here for you, acts along this first member. And the v direction acts along this second member. So we want to resolve this force along the 2 members of the system that we have here, okay? So what we want to do is I'm going to show you guys first with the parallelogram law. how we can do this. And basically, I'm going to come and say, I know I have a 600-pound force. I have that for sure, okay? That's technically my resultant, right? What I want is let me draw these. Actually, maybe it's easier if I draw it here. Let's see. What I actually want is I want some component on this axis. And I want some component of that force on this axis. Okay? So what I'm going to do here, let me see if I can draw this a little bit better. But this would be my resultant. So what I need to do is figure out how to connect these. So this would connect here. It's a little tricky drawing it the other way around, but we can do it. Okay, so this would be my F on the V. And then I would need to draw a parallel line from this point to the V axis. Something like that. And this would be my F sub u. Okay, so what I've done is I know that 600 is the resultant. I've constructed a parallelogram around that. Okay, and I just want to go ahead and do one more thing here and figure out what this angle is so that I can have everything I need to solve the problem. So I know that the top angle is 30 degrees, and I can see here the remaining section here is 120 degrees because this whole thing, right, the 30 plus the 30 plus whatever this is have to equal 180 because it's all along this bar, right? So if I have 60, 180 minus 60 is 120 degrees. That's how I got that. Okay, so now I have everything I need to solve this. Okay. That's the parallelogram. Let me actually write that here. That's if you want to use the parallelogram law. We can also use the triangle law. Again, I'll just draw that one here. We have the 600. And basically we have some FU going in this direction and some F sub V going in this direction. Okay, and all we need to do is come back here and remember that this, we can correspond that to the 30 degrees, the angle that F sub U makes with the x-axis. Then this here is the angle that F sub V makes. I know that doesn't look like 120 because the way I've drawn it. And of course, then this has to be 30, so that all makes 180. Okay? All right, so you can see actually, right, really clearly, this triangle that we just built is really just one of the triangles here. Parallelogram law. So it's really the same thing, no matter how you want to look at this. Whether you want to use the parallelogram law and use the blue shaded triangle or just go straight to the triangle, you're going to come to the same end result, which is now I need to use the law of sines. So what is the law of sines? If I look at this triangle, what the law of sines tells me is that the angle sine of the angle corresponds to the opposite magnitude. So I would say that F sub u is to sine of 120 as the 600 is to sine of this 30 here. And I can directly solve F sub u is equal to 1039 pounds. And I can do the same thing here and say F sub v corresponds to sine 30 and 600 corresponds to sine 30, and I actually just get that FV is equal to 600. Okay, so a couple of things to note here. Some interesting takeaways from this problem. Okay, the first takeaway is your resultant does not have to be the largest magnitude of your components. You can have components that are bigger than your resultant depending on what that angle is. Okay, it's dependent on what that angle is because that's what determines that proportion. Okay, so these are pretty simple and straightforward. If you just do a couple of them, and you'll kind of get the hang of this a lot more. Okay. We're going to do another example here. So this example, basically, it's giving us the required resultant force acting on the eye bolt that needs to be directed on the positive x-axis. Okay, so we don't know what F2 is, and we don't know what the resultant is, but we know the direction of the resultant has to be basically like this. Something along the positive x. Okay, and we know that this guy here needs to be minimized. We need to minimize that. We want to determine the magnitude, the angle theta corresponding to the resultant force. So what we want here is we want FR, we want theta, and for good measure, let's determine F2 as well. Okay, so I'm going to use the triangle rule here. So basically I have my resultant FR that needs to be directly in the x-axis as such. And I have some F1 that I can see acting in this direction, some F2 acting in this direction here. Okay, and I know that this angle here is 60 degrees. I don't know what this angle is, theta, it's not given to me. Okay. Now, I know that FR is equal to F1 plus F2, and I don't know what F2 is. But basically, F2 can be any vector as long as its head here is touching this line, this horizontal line. Let me show you what I mean by that. So if this is my FR here, let's say this is the x-axis, right? I know that FR has to be on the x-axis, the positive x-axis. As such, okay? I know F1, so I'm going to pull back and just draw what I know for a second. I know F1, let's say, is right here. Okay, my F2, I'm not minimizing FR. My F2 can be any vector that's going to touch the horizontal. It doesn't really matter. It can be anything. But remember, it needs to be minimum. So just from our knowledge of how the world works, if I want to get from point A to point B, what is the shortest route? Should I go like that? Should I go like that? Should I go like that? No, the shortest route is always the straight route, right? So here, this straight line, the perpendicular is going to be the minimum, the shortest F2, smallest F2. Okay, so my theta would be 90 degrees. That's going to minimize it. If that's the case, then my FR is equal to 800 cos 60, which is 400 newtons. And my F2 would be 800 sine 60, which is 693 newtons. And that's it. So pretty simple using the triangle rule to solve for these things, right? Okay, so before we get to Cartesian vector notation, we're going to stop, and this will just be part 1 of this video. So starting with part 2, we'll go ahead and get into our Cartesian vector notation and talk about setting these problems up into I and J components.